Now, let us continue with the previous lecture where we started the dual problem of a LPP. We have done one example. Let us take another example. Whenever one primal is given, how to first convert into its dual problem. Let us see this problem. Minimize z equals x 1 plus x 3 plus x 4 plus x 5 subject to x 1 minus x 3 plus x 4 minus x 5 equals to and x 2 minus x 3 minus x 4 plus x 5, this is equals to 1, and of course, x j greater than equals 0. If you see, the problem is not in the canonical form, because the problem original problem should be a maximization problem and the constant, all constants should be of less than equals type. So, this two equality constants, I have to convert it into inequality, one will be greater than equals, another will be less than equals. Then again greater than equals inequality, I have to convert it into the equality type. So, the canonical form of this one dual, the canonical form will be, and another thing, if you see, note here, since I have two constants which are of equality type, therefore, dual will have two variables which will be unrestricted in sign. So, first write down the canonical form of this problem. In canonical form of this problem means, I have to make it a maximization problem. So, maximize means it will be of minus, since you already know max of z equals mean of minus z. So, minus x 3 minus x 4 minus x 5 subject to this, I will write it as greater than equals, left hand side greater than equals to, left hand side less than equals to, and then the greater than equals to, I will make it less than equals to by multiplying by negative sign. So, this will be x 1 minus x 3 plus x 4 minus x 5 less than equals to minus x 1 plus x 3 minus x 4 plus x 5, which will be less than equals minus 2. Similarly, x 2 minus x 3 minus x 4 plus x 5 less than equals 1, and minus x 2 plus x 3 plus x 4 minus x 5, which is less than equals minus 1. And of course, your x j is greater than equals 0, where j lies between 1 to 5. So, now your problem is in the canonical form. So, from the canonical form, now you can write down its dual. Let me write down its dual here itself. That is, its dual will have how many variables in that case? Its dual, number of variables of the dual depends upon how many constants are there. Since in the canonical form we have 4 constants, so therefore, there will be 4 variables in the dual problem. So, I can write down anything, say minimize d equals, what I will do? Minimize d equals, this b values I have to take, because this b value will be the go to the objective function as coefficients of the dual variables. So, it will be 2 w 1 minus 2 w 2 plus w 3 minus w 4 subject to what will happen? Subject to, first now I have to take the constants one after another for the variables. I will take the coefficients corresponding to the variable x 1 first. X 1 is appearing only in 1 and 2 cases. So, it will be w 1 minus w 2, this is greater than equals, x 1 is absent here. So, therefore, coefficient is 0. So, w 1 minus w 2 greater than equals 0, this is 1. Next, I have to take the constants with respect to the variable x 2. For x 2, wherever it is coming, x 2 is coming on 2 places, here and here. So, it corresponds to w 3 and w 4. So, it will be W3 minus W4, that is greater than equals. Again, with respect to x2, there is no coefficient, x2 is not present in the objective function. So, coefficient is 0, W3 minus W4 greater than equals 0. Then for x3 I am having at all places. So, it will be minus W1 plus W2 minus W3 plus W4, which is greater than equals. The coefficient of x3 in objective function is minus 1. So, that it will be minus 1. Then the next one will be coefficients corresponding to the x4, that is it will be W1 minus W2, like this way I have to write down W1 minus W2 minus W3 plus W4. This is greater than equals, again coefficient of x4 in the objective function, which is minus 1, and the last one is x5, which is present in all 4 constants. So, it will be minus W1 plus W2 plus W3 minus W4, and the coefficient corresponding to this, the x5 here it is minus 1. So, therefore, this also will be minus 1, and your Wj greater than equals 0. So, this is your original problem. Now, in this one, the original problem was this, and this you are writing the corresponding dual. So, please note this one, the problem which was given to me initially, that was a minimization problem and that was of equality type constants. So, at first I have written its canonical form. Whenever I am writing the canonical form, I am making the objective function as maximization problem, whereas all the constants whatever we have taken, all will be of less than type inequality only. Then we have written the corresponding dual variable, dual problem. In dual, there will be how many variables, it depends on how many constants we are having original problem. For this particular case, I had the 4 constants, therefore, there will be 4 variables, which I am denoting this, and I have written the dual. In this problem, if you see now, in this particular problem, I can assume that W1 minus W2 equals V1 and W3 minus W4, this is equals say V2. I can assume this thing. So, from here your Wj's are greater than equals 0, and in this if you write down W1 minus W2 is greater than equals 0. So, from here if you see, first one is W1 minus W2, I am assuming this is equals V1, W3 minus W4, this I am assuming V2. So, from these constants I can write down this is V1. So, this implies your V1 greater than equals 0, V2 greater than equals 0. This I am telling from here, V1 greater than equals 0, W3 minus W4 is V2. So, V2 greater than equals 0. Similarly, the next one will be minus V1, if you take minus common, then it will be W3 minus W4. So, it will be minus V1 minus V2 greater than equals minus 1. So, next one will be minus V1 minus V2 greater than equals minus 1. Similarly, the next one will be, next one I can write down V1, this will be minus V2. So, V1 minus V2 greater than equals minus 1, V1 minus V2 should be greater than equals minus 1, and the last one is your this one. So, minus V1 plus V2 greater than equals minus 1. So, minus V1 plus V2 greater than equals minus 1. And whenever I have assumed V1 as W1 minus W2, so I can't predict what will be the value of V1, means V1 can be positive, can be negative, can be anything. Similarly, V2 also I can't say anything. because W3, W4 both are greater than equals 0, but from there I cannot assign or I cannot predict what would be the sign of V2. So, basically what happens, V1 and V2 are unrestricted in sign. So, V1 and V2 are unrestricted in sign. So, if you remember, we have told originally there was a theorem that if I have two equality type of constants, then in the dual problem there will be two variables which are unrestricted in sign. So, B1, B2 are unrestricted in sign, this we can tell. But here this condition, if you see this unrestricted in sign, this is redundant. What is the reason for this particular problem? The reason is V1 already we have told greater than equals 0, V2 is also greater than equals 0. So, this will not be there for this particular problem because of these two constraints. This is redundant and we will not use it. Therefore, the minimization problem in terms of V1, V2 we can write down minimize D equals from here 2 W1 minus W2 was there to 2 V1 plus V2, 2 V1 plus V2 subject to from here minus V1 minus V2 greater than equals minus 1, then V1 minus V2 greater than equals minus 1, third one is minus V1 plus V2 greater than equals minus 1 and V1 greater than equals 0, V2 greater than equals 0. So, like this way we can convert a problem into its dual problem. We will do one more problem, then we will go for the solution of the dual problem. So, let us take this problem minimization z equals x1 plus x2 plus x3. Here the beauty is I have all types, that is one is equality type, one less than equals type, one greater than equals type and two variables x1, x2 greater than equals 0 and one is x3 is unrestricted in sign. So, in the dual what will happen? Since I have one equality type constant, therefore, in the dual there will be one variable which will be unrestricted in sign. Similarly, since in the original problem you have one variable x3 which is unrestricted in sign, therefore, in the dual problem there will be one equality type problem, equality type constant. Now, I have to write down this one into first canonical form. Since your variable x3 is unrestricted in sign, therefore, x3 can be replaced by can be written by x3 minus x3 dash double dash, which we have done earlier itself, where both x3 dash and x3 double dash are greater than equals 0. So, that all the variables x1, x2 and x3 dash, x3 double dash are greater than equals 0 variable. So, this problem first we are writing it into the canonical form, that is maximize z equals minus x1 minus x2 minus x3 dash minus x3 double dash. So, it will be minus x3 dash plus x3 double dash subject to x1 minus 3x2 plus 4 into x3 dash minus x3 double dash less than equals 5, then minus x1 plus 3x2 minus 4 into x3 dash minus x3 double dash, which is less than equals minus 5. The next one will remain as it is, x1 minus 2x2 less than equals 3, and this I have to change the greater than equality type into less than equals type. So, minus 2x1 plus x3 dash minus x3 double dash, which is less than equals minus 4. So, minus 2x1 plus x3 dash minus x3 double dash less than equals minus 4. and of course, x1, x2, x3 dash this one x1, x2, x3 dash, x3 double dash are greater than equals 0. So, this is the problem in the canonical form. Now, once I have converted into the canonical form, I can write down its I can write down the corresponding dual problem. So, what will be the dual of this? So, in the dual there will be how many variables? Since I have 4 constants, so there will be 4 variables. So, minimize say minimize d equals the first one is 5. So, I am writing 5 v 1 dash say minus 5 v 1 double dash, then plus 3 v 2 minus 4 v 3. So, I have 4 variables v 1 dash, v 1 double dash, v 2 and v 3. So, corresponding to the constants, I am writing 5 v 1 dash minus 5 v 1 double dash plus 3 v 2 minus 4 v 3. Subject to what? Subject to I have to take the coefficients corresponding to x 1 first. So, I will start with this one subject to v 1 dash minus v 1 double dash, then here it will be v 2 is coefficient is 1, that is v 2, then for the last one minus 2 is the coefficient. So, minus 2 v 3 will be there. So, basically first constant corresponds to v 1 dash variable, second constant corresponds to the variable v 2 dash. Similarly, third constant corresponds to v 3 v 2 and fourth one v 3 v 3. So, this is greater than equals minus 2 v 3 corresponding to the problem x 1 coefficient in the objective function is minus 1. So, this is greater than equals minus 1. Similarly, we have to do it for x 2, x 3 and others. So, what you will get minus 3, I am now writing directly minus 3 v 1 dash plus 3 v 1 double dash minus twice v 2, because x 2 is appearing here, v 3 will not come. This is greater than equals minus 1. Next one is 4 v 1 dash minus 4 v 1 double dash plus v 3, which is greater than equals corresponding to x 3 dash, it is minus 1, and the last one will be minus 4 v 1 dash plus 4 v 1 double dash minus v 3, which is greater than equals coefficient of x 3 double dash is 1. So, it is 1, and where v 1 dash, v 1 double dash, v 2 and v 3 all are greater than equals 0. So, this is the problem. Now, if I assume that v equals v 1 dash minus v 1 double dash, say let us assume that v equals to v 1 dash minus v 1 double dash, then this particular dual problem I can write like minimize d equals 5 v 1 plus 3 v 2 minus 4 v 3. Just I am replacing on this dual problem, I am replacing v 1 dash minus v 1 double dash by v, by v 1, not v, but by v 1. So, here I will obtain 5 v 1 3 v 2 minus 4 v 3 subject to what? Subject to v 1 plus v 2 minus 2 v 3 greater than equals minus 1 minus 3 v 1 minus 2 v 2 greater than equals minus 1, 4 v 1 plus v 3 greater than equals 4 v 1 minus v 3. If you now see this one, this is 2 are greater than equals type. So, I can make 1 as less than equals. So, then both will be same, and if I change the value, then these two can be written as an equality type constraint. From here it is very easily we can do it. This is greater than equals is there. If I multiply minus on both sides of the second equation, then this equation will be converted into less than equals. It will be 4 v 1 dash minus 4 v 1 double dash plus v 3 which is less than equals minus 1, and the first one is 4 v 1 dash minus 4 v 1 double dash plus v 3 greater than equals minus 1. So, this less than equals type and greater than equals type I convert it and I can write one equality type constraint. So, this will be 4 v 1 plus v 3 which is equals minus 1, because ultimately this converted to minus 1. So, you see in this case your v 2 and v 3 are greater than equals 0. What about v 1? We have told what is v 1? v 1 is equals to v 1 dash minus v 1 double dash, where v 1 and v 1 dash v 1 double dash both are greater than equals 0. But we can't talk anything about v 1, because v 1 can be positive, can be negative, or in other sense v 1 is unrestricted in sign. v 1 is unrestricted in sign. So, if you remember in the theorem already we have told, if we have one variable, one equality type of constant, then in the dual one of the variable is one of the variable will be unrestricted in sign. Since we have only one equality type constant, so one variable is your unrestricted, correspondingly this one. Similarly, if you have one variable is unrestricted in sign in the original problem, then in the dual problem the constant there will be one equality type of constant, and which is true from here. If you see, we have one equality type of constant. So, I hope now you have understood how to solve, how to convert a original or primal LPP into the corresponding dual problem. Now, let us see the other one. I have a primal problem, I have a dual problem and some conclusion. If a primal problem has a feasible solution, dual problem has the feasible solution, then finite optimal solution for both will exist. So, if the primal problem has a feasible solution, dual has a feasible solution, then finite optimal solution for both will exist. If primal has no feasible solution, whereas dual has feasible solution, in that case dual objective function will be unbounded. Please note this one. If primal has no feasible solution, dual has feasible solution, then dual objective function is unbounded. Similarly, if primal has feasible solution, dual has no feasible solution, in that case primal objective function is unbounded. And if both the primal has dual, both the primal and dual has no feasible solution, then the conclusion will be for the problem no solution exists. Now, let us see how to solve a problem, how to find out the solution of a dual problem. We will come to this one later. So, this is your original problem, its dual. Let us write down what is the dual of this problem first. Dual of the problem will be minimize. There are 1, 2, 3, 4 constants. So, 4 variables will be there. So, W equals 4. I have to consider the coefficients B. So, 4 V 1 plus 6 V 2 plus 5 V 3 minus V 4 subject to V 1 plus V 3, V 1 plus V 3, this is greater than equals coefficient of x 1 in the objective function, that is 3, then V 2 plus V 3 minus V 4, V 2 plus V 3 minus V 4, this is greater than equals coefficient of x 2 in the objective function, that is minus 2, and obviously this is your problem will be this one. So, in standard form, of course, your B I greater than equals 0 for I equals 1 to 4. Now, since it is greater than equals, I can write it in the standard form, because we have solved, if you remember, maximization problem only and constants are less than equals type. So, directly I am writing this into the in standard form. So, this is the dual of the original problem. The standard form I am writing of this dual problem, maximize, say W equals, I am making a maximization problem. So, minus 4 V1 minus 6 V2 minus 5 V3 plus V4, subject to using, once I am making less than equals, I have to add the slack variables. So, V1 plus V2, V1 plus V3 minus V5, this is equals 3, and minus V1 minus V2 minus V3 minus V3 plus V4, and the slack variable plus V6. So, this is equals 2, this is equals to Vj greater than equals 0. So, here your 1 is greater than equals type, that is the reason I have here added. I will come to this later. I have just subtracted the surplus variable. I have not added any artificial variable over here, because for this case V1 and V6 will form the basis. If I make others as 0, then V1 will be 3 and V6 will be 2. So, therefore, the basis V1 and V6 will come. So, in the basis V1 and V6 will be coming, here it is A1 and A6. The coefficient values are minus 4, minus 6, minus 5, A4 it is 1. Other two variables are not there. So, it will be 0, B5 and B6 it will be 0. So, your CB will be minus 4 and it is 0. B values are 3 and 2. Now, write the rows, which is similar as we have done earlier, 1 0 minus 1 0, and this is 3 2 is there, this is 0 minus 1 minus 1 1 0 1. Zj minus Cj, if you calculate 0 6 1, this one will be minus 1, next two are next one will be 4 and this is 0. So, this is the most negative. Entering vector is this one, entering vector will be this thing. So, 3 by 0. So, you will not get anything, here you will get 2. Therefore, your departing vector will be A6. So, your entering vector is A4 and our departing vector is A6. So, from here we are making the next table. So, in the next table you will have the V1 and V4, V1 and V2 will be, A6 will be coming over here. So, I am sorry, this I have made a mistake. This will be V6 only, not V2, V6 corresponding to this, V6 is going out. So, in place of V6, V4 will come. So, it will be A1, A4, coefficient will remain same, minus 4, minus 6, minus 5 and 1 0 0. Here this is your pivot element. So, basically it will remain same. This is 1 and this is 0, already it is there. So, as such there will be no change, only Zj minus Cj value will be changing. This is minus 4, this is 1. So, it will remain same, 3 1 0 1 0 minus 1 0, this will be 2 0 minus 1 1 0 and 1. If you calculate the Zj minus Cj value now, it is 0 5 0 0 4 1. So, if you see Zj minus Cj is greater than equals 0 for all j. So, you have the optimal solution. What is the optimal solution? V1 is present here. So, V1 equals 2, sorry, V1 equals 3, V2 is not present. So, V2 0, V3 is 0 and V4 again it is 2. And what will be your W star? Your W star will become this one, minus 12 and this one. So, W star will be minus 10 basically, and I have to take the minimization. So, in unit price it will be equals to 10. If I want to find out what is the solution of the primal problem, then you take the last two columns here, because these two will correspond to the first one will correspond to the variable x1 and second one will correspond to the variable x2. So, here there was only two variables, therefore, this first one will correspond to this first variable and second one will correspond to the second variable. So, solution of original problem also I can obtain from this last table, that is you take the last columns depending upon the number of variables. So, here it will be x 1 equals 4 and x 2 equals 1 and z star, since it is minimization of this. So, the value will be this. So, please note that in the dual original problem, in the solution of the original problem, this will correspond to x 1 and this will correspond to x 2. So, this is by this way we can find out the solution of the problem. So, in the next class we will actually start the dual simplex method, because by the method which we have solved it is almost similar to your normal simplex method, but in dual simplex we have certain added advantage. So, that we will discuss in the next class.